In this section, we're going to talk about methods for sensing information about the body itself or about what's happening to the body. Let's start with the body itself. There are many aspects of body function that can be detected and used to deduce information about either the physical state of the person or about their emotional state or context. Vital signs are the signals most commonly used in medicine to get a snapshot of body function. The first of these is heart activity. How fast is the heart beating and how well is it functioning? There are a few ways to sense the heart. First, the sound of a heartbeat can be detected with a microphone. If the person is sitting very still, the movement of the skin and vessels when the heart muscle contracts can be picked up with motion sensors. The most common ways of measuring heart activity are electrically and optically. Starting with electrically, the electrocardiogram senses the electrical potential that's generated when the heart muscle contracts. 3 electrodes in a triangle around the heart will pick up a basic signal like this, and in a hospital they'll use many more electrodes so they can pick up the individual components of the heartbeat to evaluate if the heart is functioning properly. Measuring electrical signals through the skin is hard to do in clothing because the signal is very sensitive. This is what the heartbeat signal looks like under really good conditions, where dead skin has been removed and hair has been shaved away and a conductive gel has been applied to the surface, and the electrode is adhered to the skin so that it can't move. The person is also sitting very still. This is what the signal looks like if you use conductive fabric patches in a garment instead of adhering the electrodes to the skin. But the person is still sitting very still. If they start jogging, this is what happens. So you can see how easily you lose that connection between the electrode and the skin and how sensitive it is when you're trying to record heart activity. Another common way to measure heart activity is by looking at blood flow optically. If you shine a light into a translucent part of the body like the fingertips or the earlobes and catch it on the other side or as it's reflected out of that body part, the light will be absorbed differently as blood pulses through the skin. When blood is pooling before the next heartbeat, more light will be absorbed. When it's flowing right after the heartbeat, less light will be absorbed. By analyzing the colors that are absorbed and reflected, you can tell how much oxygen is being carried by the blood, which is the oxy part of pulse oximeter. This connection is a little less sensitive than the electrodes that we just talked about, but it still does need to be stable, which is why in the hospital the sensor is clipped to your finger or your earlobe with some pressure. In the doctor's office, blood pressure is measured by inflating a cuff around your arm to stop blood flow and then slowly deflating that cuff while listening to your body with a microphone or a stethoscope. The clinician or an automated system listens for the pressure at which blood first starts flowing again, which is your systolic pressure, and the pressure at which normal blood flow returns, which is your diastolic pressure. There are wearable devices that do exactly that with an inflative cuff, but it's pretty obtrusive and not very comfortable to wear. Another method uses a technique called pulse wave propagation, which measures how fast the pulse of blood is traveling through your vessels. By sensing the pulse at 2 points, like the wrist and the fingertip, you can measure the time distance between them and relate that to blood pressure. Body temperature can be measured from the surface by measuring the amount of infrared radiation that the body gives off. This can be done with a single point, or it can be done with a camera that converts light in the infrared spectrum to light in the visible spectrum. Remember that infrared temperature sensing will always sense the temperature of the outermost surface being measured, which may be different than the body's surface if you're wearing clothes. Thermometers and thermocouples often use material that changes its conductivity depending on what temperature it is. To sense core temperature, you need to get that thermocouple into the interior of the body, which is hard to do in wearable systems. Measuring surface temperature can also be useful, but as we discussed in the thermal unit, surface temperature is much more variable than core temperature and less closely linked to health. When your muscles fire, each cell produces an electrical potential as it contracts, which is measured as an electromyogram. They don't all contract together, but their electrical potentials sum up to make a signal that you can measure in much the same way as an electrocardiogram. The heart is also a muscle. That signal can be processed in a few ways and can be used to measure how hard the muscles are working. Just like the electrocardiogram, since EMG is measured with electrodes, it's also a very sensitive signal and difficult to collect in garments. Galvanic skin response is another electrodermal signal, or a signal that is measured by collecting an electrical potential with electrodes. This signal measures how conductive your skin is, which is used to detect things like emotional changes. As you get more anxious or alert or aroused, you sweat more, which makes your skin more conductive. A long time ago, GSR was used as a lie detector test, but now the polygraph uses many different body signals that are affected by emotional changes when someone is lying. Brain activity is measured using two main techniques. Using an electrodermal approach, where electrodes are placed on the scalp and used to record electrical activity through the skull, and using an approach that uses infrared light to detect blood flow in the brain, similar to the pulse oximeter. Understanding brain signals is a much newer field, so less is known about how to interpret those signals, but it's changing very fast. Measuring breathing in a clinic or lab setting involves a lot of equipment, which is used to detect airflow and volume, as well as the composition of that air. In wearable systems, you can sense breathing by detecting the expansion and contraction of the torso. If you place a few different sensors, you can sense what kind of breathing is happening, if it's in the upper chest or lower in the abdomen. Sensing that kind of expansion and contraction that happens during breathing can be done in a few ways. Some of the main approaches are using a looped conductor, using suspended conductive particles, or by adapting a bend sensor. Later we'll talk about capacitors, which are another way to sense that kind of movement. To sense stretch using a looped conductor, you need a conductive thread or a fiber that's looped on itself in such a way that when you stretch it, loops are pulled in and out of contact. Wherever loops are touching is a short circuit in the electrical path. So if you move those shorts around or open and close them, the path that the electrons are flowing through gets shorter or longer, which also means that the overall sensor gets more or less resistive. We can interpret that change in resistance as stretch or contraction. In my lab, we developed a sensor like this using the cover stitch machine. The top and bottom cover threads can both be used to make sensors if you use a conductive thread instead of a regular thread. You can also make sensors by knitting conductive threads, since knitting also makes that looped structure, and those loops slide in and out of each other as the textile is stretched. If you suspend conductive particles in a stretchy substance like rubber, as you stretch the substance, the particles are pulled away from each other. This increases the resistance of the sensor, which you can then use to deduce how much stretch happened. Finally, since bend and stretch are related, you can use one kind of a sensor to sense the other thing if you set it up right. Many bend sensors actually operate by sensing stretch. For example, one very common way to make a bend sensor is to apply a very thin zigzag trace of metal to the top of a bendy strip. As that strip is bent, the convex side gets stretched a little and the concave side gets compressed a little. When metal is stretched out like that, it gets more resistive, so you can sense this stretching and contracting as a resistance change. So you could do the same thing with any of the other methods of sensing stretch if you attach them to a non-stretch surface that bends. But remember that the amount of stretch that's happening in a bend is still very small. If you wanted to use a bend sensor like that doesn't stretch very much, to sense stretch, you could attach it to a piece of elastic or stretchy material so that it's buckled up in the relaxed position and then flattens out when you stretch it. That way you're still sensing bend, but the bend is happening because of stretch. Bend and stretch are useful to detect joint positions as well. As we discussed in the mobility unit, when joints bend, one side contracts and the other side stretches, and at least one side just bends without extending or contracting. Sensors like these can be used to sense joint movements and positions, and that information can be used to determine what position the wearer is in or what they might be doing. Another way to sense body movement and position is to use inertial sensors. Accelerometers that sense acceleration, magnetometers that sense orientation relative to Earth gravity, and gyroscopes that sense rotation are all inertial sensors. They're usually micro-electromechanical sensors, or MEMS sensors, meaning that there's a tiny mass moving around inside the sensor when it's moved, which is how the sensor detects those movements and positions. Finally, the last signal I want to talk about is compression. Forces applied to the body can tell you what the wearer is touching or how a wearable system is affecting the body, among other things. There are a few ways to sense compression perpendicular to the body surface. The first is using a capacitor. A capacitor is a set of two conductive plates that are separated by insulation or air. A charge builds up across those plates when the capacitor is in a circuit, and the charge changes depending on how far apart those plates are. So when a force is applied to the top plate, it can be sensed as a change in the capacitance of the capacitor. Capacitors can also be used to sense stretch. If you separate the two plates with a stretchy substance, as you stretch that substance, it tends to get thinner and the plates get closer, and the capacitance changes. Similarly, if you make the plates themselves stretchy, they change shape as they get stretched, which is another way to change capacitance. The second method of sensing forces applied to the body is a little more simple. In the electricity and e-textile section, we talked about switches and open circuits. A simple switch can be made by putting two conductive pieces on either side of a spacer with a hole in it, like a piece of foam or a mesh with a perforation. When the spacer is squished, the two pieces of conductive material come together, closing the switch and completing the circuit. The diameter of that hole controls how much force is needed to close that switch, so it can be calibrated to respond only at a certain amount of force. Finally, other kinds of stretch and bend sensors can be adapted to sense compression as well. If the sensor is mounted on a squishy layer, when the force is applied, it will deform into that layer, stretching or bending in that process.